So, welcome to this taster lecture in exoplanets. My name is Dr. Filson, and I'm a lecturer in astrophysics at the University of Lincoln in the School of Maths and Physics. So, this is just a taster of what you might get if you come and do a physics degree here in the School of Physics, Maths and Physics. And we'll just have a look at some basic detection methods for exoplanets and one or two of the most interesting ones that we've found so far. So as of March 2020, there's just over 4,000 exoplanets been discovered so far. This is actually a chart that we've taken from the Exoplanet archive. This is available to everyone, and it has details of the confirmed exoplanets that we've discovered so far. Now, this actual plot shows you all the different techniques that we've just used to discover these exoplanets. And you can see two quite large spikes there, and that is from the Kepler Space Telescope when they've released their first and second data sets, and you get a spike in these exoplanet discoveries. And you'll also note the colors there. The colors are the different techniques that have been used. So green is for the transit method, which is when a planet passes in front of its star and blocks out some of its light. And then the radial velocity one is the red, and you've got some other ones as well. But the most dominant ones are your radial velocity and your transit. Actually, a lot of them have come from the transit method, predominantly from the Kepler Space Telescope. It's been very, very good at detecting these exoplanets. And these aren't just single planets around a star. Quite a lot of them have got multiple planets in the system, a bit like our solar system, really. So, two main detection methods then. You've got number one, which is the transit method. That's probably discovered the most so far, and that just looks for a dip in brightness of a star as a planet passes in front. Fairly simple technique, really, but there's a lot of information you can get just by looking at the shape of that transit. We'll have a quick look at that in a few slides' time. Now, the second one is the radial velocity method, and that uses a Doppler shift in the wavelength of the star to work out any planets orbiting around it. So you may think of a planet orbiting around a star, but actually they're orbiting a common center of mass. Because the planet is generally a lot smaller than the star, it appears that the planet will be orbiting the star. But in reality, the star does have a slight wobble to it as the planet goes around. So because they're orbiting this common center of mass, the star will have a bit of a wobble. And when we look at a star, it will move away from us and toward us. And then you then get a red shift and a blue shift in that light that we receive. So you get a Doppler shift in the light. And we can measure that by using spectroscopy, and then we can work out a planet. So we can get the orbital period, the size of the planet, things like that, just by looking at this method. That's the next most significant method for detecting these planets. And then probably the third one, although when it gets past these two, there's not that many detected in the method. So the next one might be direct imaging of a planet. And at the bottom there, you actually have 4 exoplanets orbiting a star, which sounds great. But the thing to bear in mind here is these exoplanets are a long way from their star, and they're very big. So these are much, much bigger than Jupiter. They're a very long way from their star. And the reason we can see them is because they're big and they're not close to the star, because if they're close to the star will outshine them because they're not emitting their own light, they're just reflecting starlight. So let's look at the transit method then as an example. Now you might think when you look into the sky, all stars or most stars, they're a constant brightness, they don't change. Well, actually most stars will show some variability. In fact, most stars do. So you've got an idea there of a star that's changing in brightness over time. And then on the right-hand side, you've actually got that center star. There's 2 images there showing in a bit of a video, and you can see that center star is getting brighter and then dimmer. And this is an example of a variable star. So most stars are variable. They show a varying brightness over time. There's a lot of reasons for that. So one of them might be that the star itself actually pulsates. So as stars evolve and they move along their evolutionary pathway, sometimes they can actually pulsate like this. So on the left hand side, you've got a star pulsating, and you can see it's getting bigger and smaller, but also it's changing colour. So its surface temperature is changing. Now, if you were to look at that star in the sky over a period of time, that would actually just show a periodic change in its brightness. So you get a kind of plot that you see on the right hand side there. So the luminosity, the brightness of that star is going to show this nice periodic change in time. That's obviously not useful for us for finding exoplanets, although we have found planets around stars that are doing this, which raises more questions, but still. The one we're really interested in for exoplanets is what happens when a planet passes in front of the star as we look at it. So here, as that planet passes in front, it blocks out some of the starlight. So the brightness of that star will dip down for the period that it's actually passing in front of the star. Now, it would normally give us this very nice symmetric U-shaped brightness, or dip in the brightness, as you can see there. And that is really, really useful for finding out information about that particular planet. So looking at that shape of that transit, the depth of it, so how much the star is dimmed by, can help us work out the radius of the planet. So if we know how big the star is, the radius of the star, we can measure how much light is blocked out, and then we can work out the radius of the planet. So it's basically a ratio of the size of the star and the size of the planet. The bigger the planet, the more light it will block out, and the smaller the planet, the less light it blocks out. So you can see from this method already that actually small planets are going to be quite hard to find. The bigger they are, the easier they are, because they give a bigger signature or a bigger dip in brightness. Now, the actual width of that U, that dip that you get, can give us some orbital parameters of the planet as well as its radius as well. So if you're not familiar with Kepler's laws, one of Kepler's laws can be used to work out its orbital period with respect to how wide this dip is. The further away the planet is from the star, it will take a lot longer to pass in front of it. So when you actually look at Kepler's laws, and you can basically derive an equation to work out its orbital period just from how long it takes to go over the front of the star. And that would be something we would actually work through in our lectures during the module. So it can be quite useful for finding out information about the planets, and it's predominantly from this that we get what the systems look like. Now, Kepler 11 is an interesting system because it has 6 planets orbiting it. Now, remember what we just had a look at with regards to the shape of that transit. The transit of each planet is shown on the left there. So you've got A, B, C, D, E, F, which is all the different planets. And then you've got on the right-hand side the size of those planets and their configuration in the system. And you can see that each transit is different. So if we take, for example, planet E, which is actually the light or the dip D on the left-hand side, and it has the deepest transit, so it blocks out the most light. And you can see that actually in the system, it's the largest planet. It's actually about 4.5 times the radius of Earth. And then if we look at planet G, it actually has the longest transit time, so the widest U-shaped dip. And that planet is actually situated the furthest away from its star, so it's taking longer to go over its transit. So you can see from here the example of how that transit shape changes with regards to the size of the planet and where it is in the system. So it's a very powerful tool, really, looking at these shapes. Now, you're probably familiar with the habitable zone of planets, so they must be the right distance from their star to have liquid water on their surface. Obviously, the Earth is just about right, and then you have planets either side. So Mars and Venus are kind of on the boundaries of our habitable zone. So when we're looking for exoplanets, we're looking for these planets that are kind of at that right distance from their star. Now, an interesting one that was recently discovered was TRAPPIST-1. And this actually had 7 planets in it that were potentially habitable. So there was like the temperature is potentially right for water, liquid water, to be on their surface. They're quite bunched up, and they're very close to their star. So the difference here is, although they might have the right surface temperature for liquid water like we do on Earth, they're very close to their star, and their star that they orbit is very small as well. So the smaller the star, obviously, the less luminous it is, and the less energy it's giving out. So the planets have to be closer. If you've got a bigger star, they can be further away. So if you have a look at the image here, you've got our solar system there, where our planets are, and then zoomed in, right, very, very close to the star, is where the TRAPPIST-1 system is. So yes, they could potentially be habitable, but they're very close to that star because it's a red dwarf. And one thing that they don't always mention is how close these planets might be. So a lot of the planets we found that are habitable are actually around red dwarfs. So quite a lot of them are around these small stars. And a comparison to Jupiter with the TRAPPIST-1 system is quite good, really, because they're almost comparable. TRAPPIST-1, the star itself, is actually not that much bigger than Jupiter. So it's a very small star. It's almost kind of on the lower boundary of what a star can be before it's classified as a brown dwarf or even a planet. So Jupiter you've got there, and you've got the 4 Galilean moons, which are its 4 largest moons. And this is kind of to scale as well. So you can see where the moons are orbiting Jupiter, and you can see where the planets are orbiting the star. And they're almost the same sort of distance. So it gives you an idea of how small the system actually is. So they only take a few days really to orbit the star because they're so close. Now, the biggest issue with planets this close to their star when they're red dwarfs, so yes, the surface temperature might be okay to have liquid water there, but they undergo fairly frequent large flares given the size of them. And any planets that are nearby are just going to get sterilized. Their surfaces are not going to be habitable at all. And if they do have an atmosphere, there's a potential that the atmospheres can be evaporated. So I think there's been some measurements taken, and some of these stars, they've been observed to be losing their atmosphere because they're so close to their star that these flares can actually just rip away atmospheres. So although they are potentially habitable, are they realistically going to be habitable? Chances are they aren't because of these large flares that red dwarfs typically have. They're quite magnetically active, which is what causes these flares. So, I'll be a little bit careful about looking at the habitability of planets with regards to these smaller stars. So moving on to some interesting systems then. So this is probably one of the only planets that we found that is orbiting 3 stars. So it's a triple star system that it's orbiting. So on the left-hand side, you've got the red line, which is basically, or the red circle, which is the orbit of the planet. So it's basically a very large, hot Jupiter. So it's a gas giant, so it's technically not habitable itself, it's too big. And then it's orbiting a large star, which in itself is then orbiting around the outside of 2 smaller stars. So it's a very chaotic and unusual system. But what happens here is, for 1/4 of its orbit, the entire planet would be in day. So think about, what are your days going to look like on this planet? What your season's going to be like? It's a very unusual environment it's going to be. But the thing with this particular planet is it couldn't form where it is. The system's too dynamic, too unstable. So for a planet to form where it is almost impossible. But one of the scenarios for its current configuration is it might have been a planet ejected from another system that was free floating about in space, and it got too close to this triple star system and was captured. And this is, the exchange of planets or material between stars is not thought to be uncommon. In fact, we've actually had asteroids or interstellar objects pass through our own system, and there may even be objects in our system now that have been captured from other stars. So it's not an uncommon thing to occur. We then have binary systems. So 2 stars, and you have an exoplanet orbiting around them. So Kepler-16b is probably a really good example of one. You've got the stars A and B. So they are quite small stars, but combined, they're about the size of the Sun. So they're both smaller than the Sun, but combined, they're about the same mass. And Kepler 16b is a Saturn-sized planet. So again, it's a gas giant. It's not habitable itself, but it does technically lie in the habitable zone around the two stars. And the two stars are quite close together, so the planet itself isn't moving around too much. So the planet's not habitable. However, if you were to place an Earth-sized moon around that planet, that could potentially be habitable. And there's been some modeling on that, some simulations to show that it could be stable. So you could have a moon orbiting this planet that would be habitable. Again, think about what your days are going to look like, what your season's going to be like there, but it has the potential to be habitable. So these are not just in science fiction anymore, these are becoming real systems. So there's two types, or two main types of exoplanets orbiting binary multiple star systems. You have a P-type and an S-type. The P-type is where the planet will orbit around the outside of the two stars. So like Kepler 16b is orbiting around the outside of its two central stars. The S-type would be where one of the planets is orbiting, or sorry, just the planet is orbiting one star. And then those two stars would then orbit one another. Now they're typically less stable. They're quite difficult to form like that. Whereas the P-type, you can have a disk of material around those binary stars and planets can form. So the P-type is a lot more stable than the S-type. The S-type, most likely they would have been captured from objects that got too close, whereas P-type, they can form where they are. Now finally, we'll have a look at exomoons really. So moons in our own solar system are able to potentially support life a long way outside of the habitable zone. So at the moment, if we were just looking at the habitable zone around our own sun, then it's mostly just going to be Earth. We're bang in the center of that. We can have liquid water on our surface. But if you consider moons around planets, you can have liquid water. So on the left-hand side, you've got Europa, and on the right-hand side, you've got Enceladus, which is orbiting Saturn. Now, these have both got liquid oceans underneath their frozen surfaces, and these are outside the habitable zone. It's thought that some of the energy, internal energy to support that liquid water comes from tidal energy from the large planets that they orbit. So there's a potential for a lot of these gas giants we've found around other stars, although they aren't habitable themselves. If you placed a large moon around them, they could be, because we have evidence in our own system that that could be the case. And just to give you an example here, the green line would be the typical habitable zone around a star, and on the y-axis, your size of your star increases. So what that means is actually, as the star gets bigger, it gets bigger, brighter, so there's more energy there. So actually, the planets could be situated further away. But if you start to consider internal energy that can be supplied to one of these objects, you could be much further away from that star and still be habitable. So this is applicable for the gas giants and their moons. And you can see here they have to have internal heat or energy supplied, but you can be a long way from outside the habitable zone and still have liquid water, not necessarily on the surface, but you can just have a liquid ocean underneath. But the question is, have we actually found any of these exomoons or moons orbiting exoplanets? Well, it's been a bit on-off for a few years. Kepler 1625b was thought to be one of the first ones to be discovered. It was a moon the size of Neptune, so this is not a small moon, orbiting a gas giant that was 10 times larger than Jupiter. And this just proves, this is a big system and a big moon, that finding these moons is very difficult. So again, you've got that U-shaped transit from the planet passing in front of the star. But as a moon is orbiting the planet, you get a more asymmetrical shape. So it's no longer a perfect U shape. You have slight differences in it. And it's those differences that can help you find these exomoons. But as it stands right now, it's not been confirmed. We're still, on the hunt for these exomoons, and hopefully in the next coming years we're going to get an explosion in them, similar to how we've had the explosion in exoplanets in the last decade. Thank you for listening. I hope you enjoyed.